We go into the next section, talk a little bit more about advanced systems. You're not really going to find these in the knowledge test, but we're still going to test you on most of these systems on the next exam, as well as a little bit on the final. For these advanced systems, we do got your discussion page here for questions. We're going to start off with turbochargers. Turbocharger, very nice way to get more power out of the engine. When you think about the Cirrus or the Seminole, I'm flying a normally aspirated engine. So over here at sea level, I have the most power I'm going to get out of a naturally aspirated engine, given a standard day. And as soon as I start climbing, I immediately have fewer air molecules. And if I keep climbing, I keep having less and less air molecules. So the performance of my engine is degrading as I go up. And you can see that in your Cirrus performance chart for the climb. And you can see how you have a less rate of climb as you go up. Now the turbocharge engine has the ability to pack air molecules together and to maintain that 100% rated power. So we start off at sea level at the 100% rated power here, and for a while we just maintain that. Now turbocharger effect will degrade when you get high enough. We used to fly the Piper Seneca here, and it was 225 horsepower engines. They were turbocharged. They were wonderful. We would fly those airplanes, some days be doing maneuvers at 10,000 feet with students. We want to get above the clouds. So, done that, been up there a couple times doing that. It was wonderful. It was an airplane because of the turbocharger and because it had the ability to maintain its rated output. We could actually do single engine go-arounds and single engine missed approach procedures and go do a single engine hold. It would not be outside a normal day to have a student take off from Battle Creek. And as we go to Lansing, do the ILS approach, we lose an engine on the ILS approach and make the student go missed approach, one engine missed. And then we head over to the hold, get done holding, we head down to Jackson, all on one engine. Do the approach down there at Jackson, usually circle on one engine. That was a pretty typical training day for the student because we had the Seneca. Loved it. But your Seminole doesn't quite have that type of power. If you want to get the Seminole to climb, hopefully it's wintertime and really cold out, we'll get it to climb on one engine fairly okay. Right? In the summertime, there's days I've struggled to get to the pattern altitude on one engine. Difference between the turbocharged and the normally aspirated engine. All right, let's take a peek here at a couple different critters because turbocharging comes in a couple different flavors here. The first one is a turbo normalized situation. Yeah, that would be an example if you were to look at the Cirrus SR22 turbo model. They have normalized the turbocharger system, which means they're going to maintain sea level pressure up to the high altitudes. Now we think about sea level pressure as 29.92 inches, but we could just round that up to 30 inches of manifold pressure. So 30 inches of manifold. So we're maintaining 30 inches all the way up to a certain predetermined altitude. And then after that altitude, if we go higher, we'll have a decrease in the manifold pressure. That SR22 turbo model can go all the way up to 25,000 feet, which is its rated altitude, its maximum altitude, and it can maintain 30 inches all the way up. Can probably maintain 30 inches higher, but the airplane's not certified to go higher than 25,000 feet. So that's pretty good. The other one is turbo supercharging. And when we talk about supercharging, we're going to boost the pressure beyond sea level, so beyond 30 inches. Our Piper Seminole, I'm sorry, the Piper Seneca was 42 inches of maximum boost. Normal was 40 for it. All right, we had a couple 2 inches of overboost capability with it. So that was nice, and we could hold 40 inches all the way up to 14,000 feet. So that's a pretty good deal out of it. If you are thinking about doing Red Bull air racing, those engines are probably going to be doing upwards of 100 inches of manifold at a minimum. All right, and then they're probably at times where they're maybe injecting something into the system to get maybe 120, 130 inches for a brief period of time. So we're talking about some serious power on these things. Oh, and just a note, we talk about supercharging in an airplane. If you're familiar with a car supercharger, which is belt driven, we're not talking about that type of a setup here in an airplane engine. Okay, everything is going to be exhaust driven, whether it's normalized system or supercharged system. Okay? So just a real quick video here on the operation, kind of giving you an idea of the inflow and outflow of a turbocharger. Okay. What we do is we have air come in to the turbocharger, and then it hits the compressor and gets compressed. Okay. Now this red is going to be the hot exhaust gas that's turning the turbine blades, and connected to the turbine blades is the compressor section. And this is where the air, the blue, is being compressed, and then that's going out into your engine. So everything's exhaust driven on this airplane. A little simple little diagram here. So we'll have a few parts. Right? To explain the parts for a moment, we have a second here. We've got the compressor over here. That's where air comes in to the compressor. Right? That's one part. The next part is the exhaust driven turbine blade. So the turbine. Located in the system, it's not drawn here, but will be a butterfly valve connected to your throttle. And there's one other part, but we're going to talk about that on the next slide here. Let me put this in motion and show you what's happening. As air comes in to the system, it's going right through the compressor, and compressed air is going right into the cylinder. And that extra compressed air gets mixed with a little bit more fuel, and it increases the output of the engine, right? So we get more power, you get more exhaust. More exhaust is going to go through that turbine, and it's going to cause that turbine to spin a little bit faster. Okay? And then that faster spinning turbine is going to compress a little bit more air, and that more compressed air is going to go into the cylinder, and that's going to cause more fuel to be mixed with it, more power, and more exhaust. And that more exhaust is going to go over the turbine blade and spin it faster. And it's directly connected to the compressor, so it's going to spin the compressor faster, and that's going to compress more air, and that more air is going to go into the cylinder, and more fuel is going to be added in. So you're going to get more power, you're going to get more exhaust, and you're going to then have more exhaust over the turbine. It's going to spin that turbine faster. It's connected to the compressor, so more air is compressed. More compressed air is coming into the cylinder, more fuel is being added, more power, more exhaust spins the turbine faster, which spins the compressor faster, which brings more compressed air into the cylinder, which is added with more fuel, more power, more exhaust, and it just keeps going on until it reaches an equilibrium point. How long does that take? Maybe 5-6 seconds. Has to kind of spool up, is what the deal is with that. And then it reaches an equilibrium point, and then it's going to just maintain at that point there. So that is the operation of our turbocharger. We got to throw in another part to it here, and that's called the waste gate. Over here on the exhaust side, the red side, our exhaust is coming in. And the main flow is over the turbine blade, but there's also this secondary pathway to bypass the turbine. And that's what the waste gate is. It's kind of wasting the exhaust gas and bypassing the turbine with it. So let's think for a moment. When we're on the ground at sea level, I don't need a lot of turbocharger effect at this moment here. So I'm going to have the waste gate to be completely open down here at sea level. Enter a climb. Okay, take off, enter the climb. You're going up in altitude. You have fewer air molecules coming in over here to the compressor. Okay. So what we need to do is actually redirect more exhaust gas over the turbine and spin the compressor faster as we climb up. So we start closing the waste gate here to direct more exhaust gas over the turbine, which spins it faster, which allows it to take and draw in more air and compress it together to still get the needed amount of air to maintain your power setting. As you continue to climb up, the waste gate continues to close down. At some point, you'll reach the maximum effect of your turbocharger, which means your waste gate is completely closed and all exhaust gas is going over the turbine. So that's how the system is maintaining that 100% power all the way up to altitude by closing of the waste gate. Questions there? At least not yet. Let's try top hat question then. All right. Don't read more into this question than what's there. What directly spins the turbine on a turbocharger? What causes that turbine to spin? Don't read more into it than what's there. Most of you got that one. All right. The exhaust gas spins the turbine. That's right. Directly spins it. Nothing else spins the turbine. Try another one here. Again, don't read more into this question than what's there. What directly spins the compressor? What directly spins the compressor, though? Oh, wow. Okay, most of you got that one right. It is the turbine. They're connected together. Whatever speed the turbine spins, compressor spins. Exhaust gas spins the turbine spins the compressor.